Welcome back. So we are continuing the foundation part. So this week, we're moving towards the last lecture of linear models. And this whole week will cover a quite extended history of structured prediction. Structures are one of the most important problems that NLP solves. We will use sequence labeling as an example to show you the basic ideas, basic thoughts of solving structured problems. We will cover both generative models and discriminative models for sequence labeling. So you can find that these are actually extensions to our generative and discriminative text classifiers. So for today, the first two sections will be about a generative model called Hidden Markov Model, or HMM. The second part will be about a discriminative model called Conditional Random Field, or CRF. So these two models are what a student who learned NLP must know. Okay, so after this lecture and after review, I wish that all of you can say we know the principles of these two models. So first of all, let's take a look at what is structured prediction and what is sequence labeling. So in week one, we learned a lot of NLP tasks, right? There are fundamental NLP tasks, there are information extraction tasks, which cover structures. So for example, on top, I just give you reviews of the syntactic trees. On the left is a constituent tree. On the right is a dependency tree. And you can find that both of them contain interdependent substructures, right? So if you modify a part of the tree, the other parts are affected, right? So for example, if you combine, in the first example, Tim and Bot into the same constituent, then maybe Bot can no longer belong to the verb phrase on the right. Okay, so when you take the structure as an output, you must consider the substructures simultaneously. And in the table below, we also learned a lot of sequential structure tasks, such as segmentation, how to chunk a sequence into different parts, and of course, sequence labeling. So on the bottom of this table, you see part of speech tagging, which is a sequence labeling task, okay, to give each input word a part of speech, such as a noun, a verb, etc. All right, so and here are more examples. For part of speech tagging, the input is a word sequence, the output is a part of speech sequence. Okay, so take the first sentence. For example, the input is James went to the shop yesterday. And the part of speech sequence is personal pronoun, past tense verb, preposition, a determiner, and a noun and a period, a punctuation. Okay, so we're translating a word sequence into a label sequence. And the numbers of items in the two sequences are the same. Okay, so this is called sequence labeling. And we will use this as a simple example to illustrate how you solve structured prediction problems. So this tool covers chapters 7 and 8 in the book, but you will find how to solve other structures in chapters 9 to 11. Okay. All right, so we can represent the input and output in different forms. So the correspondence between every word and every part of speech tag allows us, right, to write word to tag in a sequence, okay? Or we just compose word and tag in a sequence. So these are all the ways we can represent an input-output pair, all right? So how do you predict a label sequence given a word sequence? Okay, so a very simple idea is, well, why don't we take every label independently, okay? So let's break the structured problem into unstructured problems. Let's break them locally, right? We try to predict the first tag as a classification problem. And then we predict the second one and the third one. If we go through it, we predict the tag 7 times, and we get the tag sequence, right? So this is the first idea, and I call it a local model. A local model will just take the assignment of each part of speech tag as a separate classification task, okay? And then what's the input, okay? How do you model this problem? What's the input when we predict each tag, okay? So of course we can simplify these tasks a little bit by not treating the whole sequence as the input, but only a 5-word window with the current tag in the middle, okay? All right, so the task will be simpler, okay? We have 5 words, okay? The word on top of the tag, the word on its left, the second word on its left, and the word on its right, and the second word on its right. Okay, 5 words to predict one tag. And we can denote these 5 words as I show you here, okay? I denote the left words with I minus 1, I minus 2, the current words with I, and the right words with I plus 1, I plus 2. And these are the indices, okay? 5 words to one tag. So if we have James went to the shop yesterday, when we try to predict what's the part of speech of the word to, okay, we can take the 5-word window. On its left are James went. On its right are the shop, okay, to predict this word. And now we try to build a feature-based model or discriminative model to do the prediction. How do we parameterize the model? Of course, we need to map the 5-word and 1 part of speech tag into a vector representation, input-output vector representation. And we need to define some feature templates to this end, all right? So, and the feature templates are to our decision. One very simple design is to, okay, maybe we can combine the word at every location. There are 5 words, right? We just combine every word in this 5-word window with the current part of speech tag, and we result in 5 feature templates. They are WI minus 2 TI, WI minus 1 TI until WI plus 2 TI, okay? These are a little bit different from the feature template you used to see. You used to see a feature template in WC, for example, right? Word and class label combination. But why are there subscripts to W and T? This is because we're differentiating the 5 words in a 5-word window, okay? Originally, when we're doing text classification, we don't know how long the document is, right? So we took the naive Bayes assumption. Back of word assumption, we assumed that every word is independent of each other, right? When they indicate a class label. Now we're slightly different. We're saying the word, okay, 2 words to the left of the current word, it will play a different role from the word, one word to the left of the current word, okay? So our feature template will have the subscripts, the indices, right? Okay, so how can you translate a feature template with a position into a feature instance? All right, the idea is similar to combining the class label with the word, okay? So, oh, you see the small fonts in here. So the first chunk is very familiar. Let's just take wi minus 2, for example, okay? We enumerate all vocabulary words in one row, right? And the first row, we compose every vocabulary word with the first part of speech label. Maybe that's a determiner, maybe that's a noun, okay? And the second row, we combine every vocabulary word with another part of speech label, okay? So the number of rows here equals the number of part of speech labels in the label set, okay? The number of columns here equals the number of columns, the number of words in the vocabulary. So this is exactly the same as your W and C, right? Okay, if you have a feature template, W and C, you turn that into a long feature vector of vocabulary size times the class label set size. But that's only for wi minus 2, okay? How can we integrate position into that one? The idea is, again, very simple. Cartesian product. We multiply this 5 times. The first chunk is for wi minus 2, right? And I copy and paste it. The feature vector becomes longer, right? The second chunk is for wi minus 1. Third for wi. Fourth for wi plus 1. Fifth for wi plus 2. Okay. So I'm saying that I integrated 5 position indexes into this W and C combination, right? Now we ended up with WCP combination. Okay, and our feature vector is 5 times as long as our WC feature vector. Okay, so now, when we're given this, James went to the park, okay? Which elements in here are non-zero? Which elements are zeros? Okay, let's look at the first chunk, okay, about wi minus 1. In all these chunks, only one feature instance is non-zero, right? Which is wi minus 2 is James, and ti is 2, right? 2, when we have the 2 as the output, okay? What if our output is not 2, it's nn, which means a noun? Then only the row that corresponds to nn and the column that corresponds to James will be non-zero, will be 1, right? The others will be all zeros. Oh, but this is the first block, right? We still have the second block, which corresponds to I minus 1. Okay, in this block, only the went word and the part of speech tag output is 1, right? The remaining are zeros. Okay, so again, I reinforced you about the discrete feature representation of input and outputs, okay? So this is very different from neural representation, which we will encounter next week. But let's remind ourselves of how people represent the input and output in the linear models, all right? So whatever feature template you have, okay? So it's a Cartesian product of every element in the feature templates, okay? And only the elements that correspond to your input-output pair will fire. Okay, now given the representation of the input and output, the remaining thing everyone knows, okay? Because when we have phi, then we just need to parameterize the model using a theta, right? And given a set of data with gold input and output sequences, we can train using SGD, Okay, we can train SVM, we can train a perceptron, we can train a log linear model, right? So, so that in the end we can predict the labels one by one. Okay, so but this local model has a disadvantage, which is we treat every part of speech individually, right? So our model never will consider the fact that determiner will be followed by adjective or noun. So this fact. So when we have a determiner as the previous tag, our next tag is more likely to be a noun or adjective, but not likely to be a verb, right? You don't say, the run. You don't normally say that, right? So similarly, if the previous word is an adverb, the next word is likely a verb, but not likely a pronoun, like vary him. Okay, this is unlikely. So this local model doesn't have that knowledge. And then the solution is hidden Markov model, HMM. Okay, you should proudly tell your fellow students that you know HMM, okay, at least the principles of it. Now we're trying to build a generative model, okay, to predict the tag sequence given a word sequence. The modeling target is the probability of T1 to N given W1 to N. Okay, N is the number of words in a sentence, and the vocabulary is V. The tag set is L. Okay, how do we parameterize the model? Everyone remembers. How do you parameterize a generative model? We have three tools. One is the Bayes rule, one is the chain rule, one is the probability independence assumptions. And for those of you who are quick, you are already trying to do it. So the first step, of course, is to turn the conditional probability into a joint probability by using the Bayes rule. And this is the Bayes rule. So the probability of the tag sequence given the word sequence is proportional to the joint probability of the word sequence and the tag sequence. Okay? So this is exactly as what we did for naive Bayes. So I will not repeat myself. Okay? Now, okay, the step one, I write it there already. The conditional probability is proportional to the joint probability. Now, the joint probability is further split into, okay, the numerator in the Bayes rule, okay, is the probability of the word sequence given the tag sequence times the probability of the tag sequence. Okay, so basically we use the Bayes rule to reverse this condition and the event, right? And so now I got two components. One is the tag sequence probability. Another is the word sequence probability given the tag sequence probability. Let's first look at the second one, okay? How do we parameterize a tag sequence probability? Everyone is familiar because this is like parameterizing a word sequence probability, right? You learn n-gram language model. First step, chain rule. You take out every tag and put the remaining tags as the condition, right? Second step, independence assumptions. Okay, you can assume that every tag is dependent only on the previous tag. So that's the first order Markov assumption, right? Or you can assume that every tag is dependent on two tags on its left. So that's the second order Markov assumption. And further, similar to when you're building an n-gram language model, you can put those pseudo sentence beginning symbols S to the beginning, right? So that your model contains only one parameter type, okay? So as I write on the left of this on the right of this equation. So if you assume that the sentence beginning have B symbols, then your model will contain only the product of tag bigram probabilities, right? So that's a first order model. So if you assume that there are two B's in the beginning of the sentence, then your model will contain only a trigram probability factor, okay? So it's like trigram language model, bigram language model. So this part is easy. And now let's move to the second part, okay? How do you parameterize PW1 to n given T1 to m? Again, so nothing fancy. You apply chain rule and independence assumptions. When you apply chain rule, you realize, okay, so I take every word out, okay? So every word is conditionally dependent on its previous word and the tag sequence in the condition, right? So that's the first step. Second step, independence assumption. Now we make a very wild independence assumption. We assume that every word is not conditionally dependent on the other words, okay, but only dependent on its corresponding part of speech tag. And as a result, the word sequence probability will be the product of every word probability given the tag, right? So as I show you in the last equation here. Okay, so this is the word part. And given this word part, and we put the tag part together, we can summarize our model parameterization. For the first order model, okay, the first order, like the bigram tag sequence model, the modeling target probability will be equal to the product of 1 to n, right? The tag given its previous tag probability times the word given the current tag. That's called the first order model. Second order model, still the product from the first location to the last location, right? Every tag given its previous two tags times the word given the current tag. Okay, so that's combining our simplification of T sequence and W given T sequence. Easy to understand. Nothing too far from the naive Bayes model, right? It's only that we have two components. All right. And how do we train these probability factors? We already learned that in week 3, right? So by just counting the statistics over a set of labeled data. What do I mean by labeled data? Recall in week 2, right? Supervised data contains word sequence and output sequence, right? So if we have a set of these labeled data, we can count how many times does a noun occur after a determiner, right? So we can count these probabilities. All right, so these models, again, are generative models, so we should be able to depict how we generate the word and text sequence together. And if you look at how we parameterize the model, we basically first generated the tag sequence using an n-gram tag language model, right? And after we get the tag sequence, we generate the word sequence by generating every word according to the current tag. So that's what we did. So if I draw that out, just as n-gram language models, we get these process, okay? So on the top is the parameterization, and in the middle, I have a process to generate the tag sequence using a first order Markov assumption, right? And the second part, I generate every word dependent on the current tag, okay? Okay, so every arrow indicates a probability dependence, right? Okay. Again, if you read chapter 12 on your own, the Bayesian network, you realize all these generative models are Bayesian networks. But why is it called a hidden Markov model? Okay. The idea is the input is a word sequence, right? So you see the word sequence. You don't see the tag sequence. You want to predict the tag sequence. The tag sequence is the Markov chain, right? Every tag is dependent on the previous tag. So the tag sequence is hidden and it's a Markov chain. So that's a hidden Markov model, okay? HMM. That's the first order model, and you have the second order model as well, okay? Every tag dependent on two previous tags, all right? So, and of course, you know, we have two types of parameters, right? One is the tag n-gram parameter. We call that a transition parameter in tradition. One is the generation of a word given a tag, so we call that emission probabilities. Okay, two parameter types. We just give them different names. All right, so, okay, very similar to naive Bayes. And we finished the prediction of a tag sequence. And why do hidden Markov models consider tag-tag dependencies? Because we have the n-gram tag language model, right? So we can generate tag sequences just as we generate Shakespeare, right, in week 3, okay? And I already mentioned to you how to train such models. We have two types of parameters. One is emission probability, one is transition probability. And both of them can be trained by counting relative frequencies, okay, when we have the word tag data. So how do we train the probability of a word given a tag? So we count the number of times in our data set, okay, this word is given this tag, divided by the number of times we see this tag in the data set, right? So that's how we train a conditional probability. And how do we train tag bigram, tag trigram probabilities? Oh, we have already learned bigram, trigram language models. So it's the same, right? We only count tag bigrams, tag trigrams, and we can count these probabilities. And of course, you need smoothing. I think in your labs, you all know the importance of smoothing, right? And then good, you can build a hidden Markov model sequence labeler, part of speech tagger. That's great achievement. But you will soon find that, okay, these parameterization tricks are easy. And this training method is easy. But now we're given a word sequence. James went to the park yesterday. How do you find its part of speech sequence using your model? Okay, so that's called decoding. Wait. Why is it called decoding? Isn't finding the most probable output trivial? That is trivial when we do the classification task, you know. When you're given a document, you want to know its class label, then what do? You enumerate all possible class labels, right? And you calculate the PDC, the joint probabilities, okay? And who has the highest probability? Who is the output? Now you can do the same. Why don't we do the same? Given a word sequence, why don't we just enumerate all possible tag sequences and choose the most probable tag sequence? That's it, right? Why do you call it decoding? Now let's imagine there are L tags, right? L tags. And there are n words in the sequence. My first question is, how many tag sequences do you enumerate? How many? First location, L tags, right? Second location, L possible tags. In the end, how many? L to the power of n, right? So n is in the exponential part, right? As a result, this algorithm is called intractable. You know, only polynomial time algorithms are tractable, unfortunately. So that's why it's non-trivial, okay? We cannot enumerate all possible tags, especially when the word sequence is long. So how do you solve the problem? Okay, you learn a lot of algorithms to that end, okay? Best first search, depth first search, A-star search, dynamic program. Okay, I directly tell you the result. Dynamic program works, okay? Now we try to build a dynamic program. Okay, so this is an algorithm exercise, okay? So our goal is to find the highest scored text sequence given a word sequence, right? And we want to find a dynamic program which can run in polynomial time. Okay, to find this, okay, among an exponential number of text sequences, one that has the highest probability. Okay. Okay, and you all know that if you want to achieve that, you must be able to find your output incrementally, right? Step by step. Every step you find an optimal subproblem. You know, all dynamic programs work in this way, right? You build a table from left to right. Maybe you solve the first word first, and then you solve the first two words, and then until, okay, in the end, you solve all the words. And we have our model like this, okay? Our model scores a text sequence as a whole, you know, using this equation. And you immediately realize, okay, so this is factorizable. Why is it factorizable? Because there's a product, right, from 1 to n. Okay, now the next thing to find is, how do we find optimal subproblems? Which means, when we try to find a highest scored text sequence, can we try to find the highest scored subsequence first, and then we can incrementally find the highest scored sequence from first word to the last word, okay? Okay, let's factorize this model probability first, okay? The total product, I can take the last word out, right? The emission, the transition probability, I take them out, okay? And I name the remaining part the probability of the first word until the n-1 word, the first tag until the n-1 tag, okay? Let's just assume that the last word and tag pair doesn't exist. James went to the park yesterday. No period, okay? So the period stuff is here, right? Emission and transition. All right. And we can do that again, right? Incrementally. James went to the park. No yesterday. Okay? Yesterday is here, right? Yesterday is here. Okay? Emission, transition. Okay, now you know we can do it the same for every word. If you try to decompose a word, okay, you take the emission transition for the word. Until when? Until you got the first word, right? Until you have the first word. The first word is only one emission probability, is it? No, but you can think about the previous word, T0, as the beginning of the sentence. Then it's emission times transition again. Okay, so all we did is we sort of summarized this thing into an incremental part, and at every incremental step, we have the emission and transition, and then the previous sequence. Okay, now my question comes. My question is, if you want to find the highest scored sequence until location I, okay? Is it enough if you just find the highest scored sequence until I-1? So if someone already say no, okay? So if you can do that, then it's very simple, right? You just incremental, add every tag, and you're finished. Okay, let's denote the highest scored sequence until I as t hat 1 to I, okay? So my question is, does t hat 1 to I contain t hat 1 to I minus 1? And you all say no, right? Why is it no? Okay, it's because the incremental part has something to do with ti minus 1, right? I'm just using the first order model here. Second model is even more complicated, okay? Okay, it depends on ti minus 1. So it's possible that you find some t prime 1 to I minus 1, okay? T prime 1 to I minus 1 is scored lower than t hat 1 to I minus 1, okay? But it has a t I minus 1 that is so nice, so strong, so elegant, that allows this incremental part to be so large, okay, to overwhelm the incremental part for t hat 1 to I minus 1, okay? So which means a not so optimal subproblem leads to optimal problem. So our model failed. Okay, how do we fix it? Okay, so for those of you who are quick, dynamic program signature, you need to take into account this ti minus 1, right? So if I cannot make sure that every ti minus 1 will lead to a great new sequence, why don't we just remember them all? We add ti minus 1 into our dynamic programming signature, right? So which means we don't just store t hat 1 to I minus 1 anymore. We store t hat 1 to I minus 1 with all possible ti minus 1. If we can enumerate, okay? We cannot make sure that which one leads to the best sequence here. Why don't we just store every one of them, okay? So I change the notation. Okay. All right. So this is what I just repeat earlier. Okay. A sub-optimal problem can lead to an optimal new problem. Okay. So t prime, the issue about t prime. So we can have a t prime 1 to 3, which is lower than t hat 1 to 3, but which leads to t hat 1 to 4. Okay. So to solve this problem, we change the notation a little bit. We make sure t 1 to I bracket ti equals to t. What do I mean? I mean I store a sequence, okay, and I differentiate the sequence by the last tag, right? I store all possible subsequences 1 to I, okay? Each one with a separate ti. I can do that, right? And you suddenly realize, okay, if this is true, then, okay, among everyone that ends with now, okay, the optimal one must be contained in the optimal longer sequence. Okay? So I'm adding a constraint, right? I'm adding a constraint that t hat 1 to 3, where t3 is equal to now. Okay? If this sequence is contained in t hat 1 to 4, some constraint, okay, then you cannot find the t prime 1 to 3 where t3 is also a noun that leads to something better than what t prime 1 to 3 where t3 is a noun can lead to. Okay? What did we add? Well, I added a dynamic program signature, right? I added a constraint that if you know the last tag there is no way a suboptimal substructure will beat the optimal substructure anymore, because the incremental part contains only T3, okay? So if T3 is fixed, then your T prime cannot beat your T hat anymore. So I fixed this problem, okay? So it means that I have to take the pain to remember, okay, the subsequence with all possible last tags. I need to check which one leads to a better one, which one leads to a better one, to find, okay, this new optimal subsequence. All right, I increased the dynamic program signature to address the optimal subproblem issue. If you don't immediately catch me, I think the majority of you already caught what I mean. If you don't immediately catch me, there is an exercise for you, okay, to prove this is optimal subproblem, okay? You just need to prove by contradiction. All right. So, okay, I already found the optimal subproblem. Now the only thing left is for me to build a table, right? From left to right to remember the highest scored subsequence given this constraint, okay? So I just need to remember the highest scored subsequence with all possible last tags, right? Okay, so what is the table structure for dynamic programming? Of course, I need n columns, right? Each column means a subsequence length. How many rows do I need? Because in every subsequence, I need to remember how many different things. The tag set number, right? I need to remember all possible last tag. So I'm building a table with n columns and L rows, all right, to store the high scored subsequence score, okay? I call this table TB, okay? So TB will store, okay, the score of T hat 1 to n, where the last tag is T, okay? But only storing the highest score is not enough. I also have to score where the highest score comes from, okay? This is called back pointer. So I need another table called BP. I will give you an animation to show you how this works. Okay, for simplicity's sake, okay, let's assume that there are only two tags in the tag set, the noun, the verb, all right? And also let's assume that there's no emission probability. All the emission probabilities are 1. We only care about the transition probability, okay? And let's assume that the input is people like books, okay? And I can draw the search space in this lattice, you know. From the beginning, the people can be noun or verb, okay? Like can be noun or verb. Books can be noun or verb, right? And our table is here. There are two tags in the tag set, so 2 rows. 3 words in a sentence, so 3 columns, right? All right. All we need to do is to remember T1 to I, where Ti is equal to a tag, okay? So T1 to 1, T1 is a noun or verb. 1 to 2, T2, okay? So this is table structure. So let's begin. The first step is to fill the first subsequence, T hat 1 to 1, where T1 is a noun or verb. So this is easy, right? The previous tag must be the beginning of the sequence. So T1 is just the probability of noun given B. Now T1 with a verb is just the probability of a verb given B, okay? I just record them in each slot. Okay, there's no need for any comparison. But now, we're moving to the second word. We're trying to store the highest scored subsequence from 1 to 2, where T2 is a noun or verb. Let's first look at when T2 is a noun, okay? So when T2 is a noun, we need to look at the two optimal subsequences, right? The noun can come from a noun-noun transition, right? The noun can also come from a noun-verb-noun transition, right? Okay. So, but we can sit back being assured that this T1-to-1 noun is already the highest sequence, 1-to-1 noun. Also, this 1-to-1 verb is already the highest scored, okay? So I just need to compare this score times this noun-noun transition score, and this score times this verb-noun transition score, right? I just take the higher scored one. So noun-noun wins. So I take the noun-noun transition here. Okay, the new score, I put it here. But this noun comes from this noun. I take it down here, right? Okay. And similarly, I can take down this, the second tag being a verb, right? So I compared the noun verb and the verb verb, and I realized noun verb is better, so verb points to noun in the back pointer. So similarly, I can do the third step. The third step, okay? Okay, 1, 2, 3. T3 is a noun. There are only two paths to arrive here. Either from T2 is noun to noun or verb to noun. Hey, why don't we care about T1 anymore? Well, that's the idea, right? We already proved. Well, we know the best sequence with T2 being a noun, we don't need to look at T1 anymore, right? So we'll compare this number times noun to noun transition and this number times verb to noun transition, right? And we find that, okay, the verb to noun transition wins. So we take this here. And here, the back pointer points to verb, okay? And similarly, I fill T3 with a verb as the ending. All right, now after we are done, we need to compare the best sequence with the T3 being a noun or verb, right? We realize the best sequence with T3 being a noun wins. And then what do? We need to trace back, okay? I know that this slot has the highest score. We already know the highest scored sequence. How do we recover the sequence? From noun, we found the verb. From verb, we found the noun. Okay? Done. Noun, verb, noun. Okay, so this is the dynamic program. Okay, so we're done. So let's take a summary before the break. Okay? So I just shared with you, right, how to parameterize the generative model for sequence labeling. And that's called hidden Markov model. The parameterization is very familiar to you now. The only thing, the only trick, the only new stuff I told you is how to find the highest scored text sequence given the word sequence. That's not too difficult. That's the dynamic program. The dynamic program builds two tables, okay, with n columns and L rows. So when we build every row, we need to enumerate the previous L cells, right? So it's n times L times L. So the complexity is polynomial, okay? It's shown in the first row. All right, so now it's done. So you just tasted how to build a generative model for sequence labeling. If you're interested, you can read chapter 10 for how to build a generative model for tree generation, for parsing, okay? Now, let's look at discriminative models. The difference between generative model and discriminative model is that generative model only cares about how to generate the structure. But the discriminative model makes use of a feature representation, right? and a set of parameters to differentiate correct outputs and incorrect outputs. Okay. So actually I discussed a discriminative model earlier, which is a local model. We only care about how to predict every tag. And I said that the local model is too simple. It doesn't consider tag-tag transitions. So I will first share with you a less local model. Okay? So by treating the tag-tag transition also as a factor. And this model is called maximum entropy Markov model. Okay, I think you can already guess how it works. By saying maximum entropy model, we're saying, okay, maybe I build a log linear model to predict every tag, okay, as a classifier. But when I say Markov, well, it's just that when you predict the tag, you consider a Markov chain between tags, okay? So that's called maximum entropy Markov model. Okay, but so how do we model the generation of a tag when the previous tag is a factor? So I do some trick, okay? I don't assume the naive independence case anymore. But I assume that every tag is conditionally dependent on a previous k tags. So basically, k's order Markov chain, okay? So with that in my mind, okay, I simplify the modeling target, the probability of the tag sequence given the word sequence, into a product of every tag probability using the chain rule again, okay? But now, let's assume every tag is dependent on k minus 1 previous tags. So this is the independence assumption. This is the independence assumption, okay? A very simple trick, right? And now we got the model to build. It's not to predict every tag independently, but to predict the tag given the word sequence and the previous k tags. K minus 1 tags. Okay. Now to build this model, technologies we use are similar to the building of an extremely local model. Okay, so this is less local. How do we do it? Okay, so this is very familiar. So PTI given T, okay, previous k minus 1 tags and the word sequence is equal to, okay, just softmax theta dot phi, okay? But now the phi is extracted not from a 5-word window and the current tag, but from all the words in the input and the previous k minus 1 tags as well. All right. Okay, so you see that when we build a log linear model, only the representation changed, okay? The parameterization doesn't change. Okay, again, so now let's look at the representation. How do we represent one tag, k minus 1 history, and the word sequence? And we already know the technology, okay, which is to define a set of useful features to this end. I give you 6 feature templates to define the feature. Now it's even more than the 5 feature templates I showed you earlier, right? The 5 feature templates are actually contained in these 6 types of feature templates. Can you find where they are? Yes. Row 4, right? Row 4 lists the 5 feature templates we used to have. So, but what is row 1? Row 1 is the transition probability, right? Corresponds to the transition probability. Row 1 is just the tag transition. And here, you know, what kind of Markov assumption am I making? I'm making a first order Markov assumption, right? Okay. I'm saying that k is equal to 1. Okay, I need to correct myself a little bit. I'm assuming that every tag is dependent on the previous k tags. Okay, not k minus 1 tags. Okay, so k is 1. So this is first order MEMM. So first feature template is just the tag transition. Second feature template, what does it mean? It just means, okay, absolutely how frequent is a part of speech. But we all know that the noun, the verb are more frequent than the adverb, okay, or the adjective. So this one shows, okay, the prior knowledge about the tag. And okay, the third row and the fourth row added together, 5 patterns are what we had for that extremely local model without considering tag-tag transition. What about the 5th and 6th row? Okay, so this shows you the advantage of a discriminative model because we don't need to generate every tag only once. We don't need to generate every word only once. We can extract the prefix of a word and combine that with a tag by the intuition that maybe ing normally means a gerund or a noun, right? Okay. So, so we extract 1 letter prefix, 2 letter prefix, 3 letter prefix, 4 letter prefix, 1 letter suffix, 2 letter suffix like er, okay, and 3 letter suffix ing, 4 letter suffix, okay, etc. And I combine that with the tag. The 6th feature template is even more interesting, okay? The hyphen wi means whether wi contains a hyphen. If it does, okay, the value of the function is 1. If it doesn't, the value of the function is 0, okay? And also the case. You can define the case as, does it start with a capital letter, okay? Is it all capital letters? Or is it camel case, capital lower, capital lower? So, and so case can be a binary valued function or a multiple valued function. And in the end, you know, the feature vector will be very long, okay, with different sections corresponding to different feature templates here. But you have to, you notice one thing. Every feature template is associated with TI, okay? Is there a feature template without TI? No, because we need to represent the input and output, right? If I only represent the input, the feature template is useless. All right? And then so given a sentence and a tag and its previous tag, we can extract feature templates. All right. So this is the model. The box shows us what the model considers. But the box on the words are smaller than what I draw here. It depends on what kind of word features do we extract, right? So from this table, we only extracted like 5 word window features. So this box should be only from the -2 to +2 in this feature template, okay? But if the feature template is richer, maybe the range is larger. The training objective of this local model is to maximize the log likelihood of our data, which is to maximize the probability of every tag given its previous tag, right? Suppose that we have a data set of word and text sequences. So how do we optimize this training objective? Is to use SGD. And the detailed algorithm, we already saw it in week 5, right? To train a log linear classifier. Okay, so again, from the classification point of view, this model is nothing tricky. It's almost what we have learned. The only difference is the feature representation. Okay? So only the previous slide is worth looking at again. Okay? The remaining is the same. How to train it is the same as the classification model. All right, if you want to review it, you can read the textbook. Now, decoding is again a non-trivial issue now. When you have an extremely local model, you predict every tag independently, you don't have the decoding issue. But now, because your tag is dependent on the previous tag, when you try to find the highest scored subsequence, you cannot do every tag independently, right? Because your highest scored sequence might consider the tag-tag transition as well. How do you solve the problem? You notice that our tag-tag transition is a Markov chain. And as a result, our model, the sequence probability can be factorized into individual tag probabilities, a product, okay? And you realize there's a chance for you to find the optimal subproblem when you build this optimal problem sequence. The reasoning is very, very similar for hidden Markov model, all right? So when you build the highest scored subsequence from 1 to 4, okay, you want to find it must contain what kind of optimal subsequence from 1 to 3, right? Maybe originally you assume that, okay, t hat 1 to 4 just contains t hat 1 to 3, no matter what it is, but you realize, no, because we are a first order Markov chain, right? So the last tag here will affect the incremental score from T1 to 3 to T1 to 4. Okay. So you want a dynamic programming signature that wraps the transition inside, right? So the signature will be T hat 1 to I, where Ti is equal to any particular tag. Okay. So if you remember T hat 1 to I, with Ti being all possible tags, you can find T hat 1 to I plus 1 with Ti plus 1 being all possible tags. All right? So the signature is the same. So the table drawing process is the same. And I show you once again. Okay? So this is the reasoning process. Denote T1 to I, Ti equal T, to be a tag sequence where the last tag is T. Okay? So you can prove that T hat 1 to I, okay, Ti is T, Ti minus 1 is T prime, must contain T hat 1 to I minus 1, where ti minus 1 is t prime. You can prove that by contradiction. All right. As a result, you can rest assured that by building t hat 1 to I with ti equal to t incrementally from left to right, you can find the highest scored text sequence. And this table has the same structure as the HMM dynamic programming table. Okay, it has n columns, okay, and L rows. Each cell stores the value of the probability of t hat 1 to I, okay, 1 to I, where the last tag ti is equal to a specific label. All right. And when you try to fill t1 to I, where ti is a label, you only need to consider ti minus 1, right? So you need to take every value from the previous column and add the transition as the blue arrow shows and compare the highest scored one to be stored here. And you have a B back pointer table to store where it comes from. Okay. All right. So we built a discriminative alternative to HMM. Okay. So in HMM, you know, the incremental part is an emission and a transition, right? These two probabilities are trained separately. In MEMM, this transition is a single log linear classifier, okay? Ti given ti minus 1 and W1 to n. Okay, so the structure of the two models are highly similar. It's only that the training is different. Okay, one by SGD, one just by statistics. All right, so MEMM is strong competitive to HMM, but that's not the end of my story today. I'm telling you that there is a bug in MEMM, okay? Which also means that there is a bug in HMM. What is it? You know, there's sort of a discrepancy, okay, between the training scenario and the testing scenario. What do I mean? So when we train the model, we use the maximum likelihood estimation, right? What did we maximize? We maximize the probabilities of every tag, right? Given the previous tag and the word sequence, that's what we did, right? So the modeling target is what we try to maximize. But during decoding, what did we try to maximize? We tried to find the highest scored tag sequence, okay? All right, so I'm trying to say this global sequence level probability, if it is obtained by accumulating these locally optimized probabilities, then we have a bug. So in the end, if your decoder tries to find high scored probability here, okay, then when you maximize the log likelihood, you need to maximize this log likelihood, okay? Not the factor likelihood. That's what I claim. Okay, but some of you nodded. But I'm sure you nodded without understanding why, okay? You nodded because I said it, because this is intuitive. You want to find the highest score at something, you want to better train on that, okay? I thought and thought, and in my textbook, I found one example. Let us assume again that there's no word sequence, no emission, okay? And let us assume that there's only a first order Markov assumption, okay? Every tag is dependent on only the previous tag. And furthermore, let us assume that there are only L1, L2, and L3 in the tag set, okay? No word, no emission, only transition, only first order transition, only 3 tags. That's all the assumptions, okay? And now I coined a set of training data, okay? It's 6 documents, D1 to D6. D1 is L3, 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 okay? D2 is L1, L1, L2. Similarly, we have L1, 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 L3, L1, L1, L3, L1, and L1, L2, L2. Okay? And you find that L1, L3, L1 exist twice in the training data, right? The others exist only once. Now, I want you to compare the probability of D4 and D6. L1, L3, L1, and L1, L2, L2, okay? Now suppose we're trying to optimize the sequence probability globally. Every one of you can immediately say L4 is more probable than L6, right? Because L4 and L5 are the same. So the probability of L4 is a third. It's twice the probability of L6. That's obvious. Now let's build a local model. What do I mean by local model? A local model will calculate the sequence probability as a product of tag transitions, right? Bigram model. So what are the parameters? Ti given Ti minus 1, right? Now because we only have 3 tags, okay, and maybe a B, beginning of the sentence, we can estimate every parameter instance here. How many parameter instances do we have? 3 times 3 plus 3, right? 12 parameter instances. Okay. Can we verify? Given B as the previous tag, okay? What's the probability of L1? You tell me. How do you calculate it? You just see how many times a sequence starts with L1, right? It's 5 out of 6. What about L2 given B? Not. 0. What about L3 given B? 1 out of 6, right? So you can do the same for all the other probabilities. Unfortunately, I don't have time to calculate together with you everything, okay? But there's one thing you note. How about, let's look at PL2 given L2, okay? If the previous tag is L2, what's the probability of all tags? Now, how do you count this probability? You need to find, okay, how many times L2 is followed by another tag, right? divide it using L2 followed by L2. And you realize L2 is only followed by L2, nothing else. So P L2 given L2 is 1. All right. So anyway, we got this table with 12 cells. Now let's compare, D4 and D6 again. D4 is L1, L3, L1, right? So to calculate its probability is L1 given B times L3 given L1 given L1 given L3, right? Let's just take the 3 cells from the table, and we get 5 over 36 is the probability. How do we calculate the probability of D6? We do the same, right? We multiply all the bigram scores together, and we got 5 out of 18. Hey, you see an issue. What's the issue? If you look above, obviously D4 is twice as probable as D6. But if you look below, D6 is twice as probable as D4. Okay? That's what I mean by the discrepancy. Okay? So when you maximize the probability of every tag individually, you arrive at a different high-scored tag sequence compared to globally. Okay. And I can tell you the cause of this thing. It is because the transition from L2 to L2. It's unfair. So whenever you predicted an L2, okay, your model will tend to predict L2 to follow it in order to maximize the tag sequence probability. Okay? So this label transition, this local label transition, if your model is trained to maximize these local probabilities, it will cause a bias, okay, to favor a local transition with a high probability. That's called the label bias problem, okay? All right. So the probability of L2 to L2 transition is overestimated when you train the model locally. Because they are not comparing fairly globally together. We're only comparing whatever follows L2 locally. So I cause this bias. This is also true for hidden Markov models and our n-gram language models, okay? I will show you later there are other language models to fix this issue. But in order to solve this problem, we need to take the whole tag sequence as a unit, okay? And we want to optimize the probability. This is the conditional random field, CRF, which dominated the structured prediction problem over many, many, many years, okay? It's until 2015 that the first neural method beated conditional random field. Okay. So let's compare the idea of conditional random field with MEMM. The picture on top shows you MEMM, okay? We maximize the tag probability given the previous tag, local model. Conditional random field is another feature-based model. We optimize the whole tag sequence probability as the training objective. okay? So I'm taking the probability of T1 to n given W1 to n as a whole, right? I build a model on that. And I build a log linear model to that, okay? So CRF is a log linear model. How do we parameterize the model? We all know how to do it. The probability is equal to softmax theta dot phi, okay? So phi is a feature representation of the word and tag sequences. I call it a global feature vector. And then the parameterization is the same as when we do classification, okay? It's a softmax function. Okay, but this seemingly naive softmax function is not so simple. Do you know why? Because the denominator is an exponential summation, right? When we do softmax, you know, the numerator is simple, right? E to the power of this thing. But the denominator is the sum of all possible tag sequences e to the power of that thing, okay? So that by itself is intractable to compute. I'll come back to that later. But first, let's look at how to calculate a global feature vector and how to do decoding, okay? Okay, how do you represent the text sequence given a word sequence? Okay, we can accumulate the representation of every tag given its previous few tags and the word sequence. Why do I want to do that? Okay, I'll show you later. I want to make decoder and training tractable, okay? So in other words, I can build a CRF using exactly the same feature templates as MEMM. I can write the global feature representation as the sum of local feature representation for every label, for every tag, okay? So this big phi tag sequence word sequence is equal to the sum of small phi every tag given the word sequence and previous tag. First order conditional random field, okay? All right, so the feature templates can be the same. This is easy to understand, right? Okay, then how do we accumulate local features to represent the global sequence? Here it is. Suppose that the input is the man went to the park, period, okay? So the man went to the park, period. 7 tokens. So I can extract a local feature vector at every token. So the feature for representing T1 given T0 and W1 to 7, right? It's about the and the determiner, right? So we use the same feature templates as MEMM. Do you remember? Tag-tag transition, right? Single tag, the 5-word window and tag, prefix and suffix and tag, hyphen and case for tag. Okay, I got a long vector here. And T2 given T1, I got another representation vector. Until the last tag, okay? I got 7 feature vectors, each one to represent one tag, right? And then what did I do? What did I do? Look at the previous slide. I summed up them together, right? I summed up them together to arrive at the global feature vector. That's what I did. In other words, does the feature vector length increase? No, it doesn't increase, right? Then what increased? The feature instance counts, the non-zero counts increased, right? So in other words, I'm just treating this global feature vector as a bag of local feature vectors. I'm just saying, okay, this is a nice tag sequence because in it, there is a determinant to noun transition, there's a noun to verb transition, and there's a verb to noun transition. I added them together, right? Okay, if the sentence, the sequence contains a lot of nice patterns, it's a nice sequence. If the sequence doesn't contain a lot of nice patterns, it's a bad sequence. So that's how I accumulate local features to a global feature. Okay? All right. Now, let's compare the conditional random field feature vector and the maximum entropy Markov model feature vector. So both are log linear models. The difference is that MEMM treats every tag as a single unit, but CRF treats the tag sequence as a unit. Okay? Now, suppose that we already found a model. You already found the model. How do we find the highest scored tag sequence given a word sequence? Decoding. Well, you know, because softmax is a monotonically increasing function, so to find the highest scored softmax of something is similar to the finding of highest scored something. This is the same for classification. So we don't need to find the highest scored softmax probability. We only need to find the highest scored theta dot phi, right? Okay, but if you can only compute things to this step, it means what? It means that you need to enumerate all possible output and compare theta dot phi. It's intractable. Exponential number of outputs. So can we break theta dot phi into small factors so that we can use a dynamic program? Can we? The trick is at phi, right? Because you're global, the representation of the sequence is the sum of the representation of every tag. So theta dot sum phi is equal to sum theta dot phi distributivity. And your model scoring can be incremental. Okay? All right. So if I want to find the highest scored theta dot big phi, I can try to look at the highest scored theta dot small phi accumulated together, right? So what is this theta dot small phi at every step? Again, oh, this cannot be more familiar to you, okay? So I repeated that for HMM, I repeated that for MEMM, and you realize because phi is the same as the phi for MEMM, right? So this incremental part, theta dot local phi, has the same range as for MEMM. The incremental part only concerns 2 consecutive tags, right? So the highest scored T1 to 4 cannot contain the high score T1, 2, 3 because the incremental part concerns the last tag T3, okay? So if this one is not optimal, so why don't we store all possible last tags? T3 is noun, T3 is verb, etc. If everything is stored, then I can rest assured that this one will come from one of them, at least, right? Yeah, so again, you can prove, you can answer 3 questions by knowing one, right? 1 stone, 3 birds, okay? So again, you build an incremental table, and this table has the same structure for HMM, for MEMM. So this is a table of n columns and L rows, okay? When you fill every cell, you rest assured that, okay, you don't have to care about anything beyond the previous column, right? And you just need to enumerate everything here. You enumerate the last tag. Compare the transition, okay, this score plus the transition, okay? Find the high scored one, that must be the highest scored subsequence. So the only difference between the decoding algorithms for the 3 model is the incremental part, right? One is emission times transition. One is, okay, the theta dot phi probability, right? The probability, a softmax theta dot phi. And this time, it's simply just theta dot phi. And all these 3 algorithms are named after the famous American mathematician Andrew Viterbi. Okay, so these are called the Viterbi algorithm. Now, the only thing left is training. Unfortunately, because I condensed the whole thing into one lecture, I don't have time to write how you derive the training algorithm with you. But I only tell you what's the trick, okay? Training a log linear model is not very far from you because you already trained log linear classifiers. What you did is to use SGD and you just plugged the gradient over every training instance into the framework. You got something similar to SVM, similar to every instance of a neuron. So we will do the same, okay? So when we do the same, we first find the log probability, log likelihood of the data set, which is the sum of log probability of every training instance. And this equation is exactly the same as your log linear text classifier model. Exactly the same. Where is the difference? The difference is the summation. The summation is exponential accumulation, right? It's not simple. So, how do we solve this problem? Okay, before we go to how to solve the problem, we have to take the gradient of this thing with respect to theta, right? And this whole process is again the same as doing classification. The gradient is equal to phi, the feature representation of the correct output, right? Minus the expectation over all outputs, okay? The probability of the output times the feature of this output. That's the same. But for classification, this thing is trivial. For CRF, this thing is intractable. How to do exponential summation function? Okay, again, just summing up all the global feature vectors is exponential. But mind that every global vector is the sum of local vectors, okay? So we can replace the global feature vector with the sum of local vectors, okay? So the sum over all possible output, the sum of over all locations, the local vector, right? Okay, commutativity. swap the two sums. Sum over all locations, okay? Sum of all global sequences, the feature. That's an expectation, right? I'm saying I'm summing over all locations, okay? And I find the expectation of the local feature vector at this location over all possible output sequences. That's the intuition. And that's equal to the sum of all the locations, the sum of all the local tag bigram probabilities, okay? The local probability expectation over the local feature. I leave the proof to you. Okay, so your model calculates the global sequence probability, and you're asking for a local tag probability. What is this? This is called marginalization, right? You know the joint event of all tags. Now you're calculating the tag bigram probability. So you need to enumerate all possible locations elsewhere, right? And sum up the tag sequence probabilities. This is called marginalization. This is something I don't have time to tell you. But if you read the textbook, you can find a dynamic program to that end. Okay? That's called inside-outside. I'll leave you here. And I just showed you the trick of training conditional random field. If you assume that you know this trick, then you know the whole of CRF, okay? So that's why I say you can proudly tell your classmates you know CRF and HMM, okay? So this is something you want to know, but maybe this is something you do not use in your project because I guess most of your lab projects are LLM related, I guess. Okay. So, okay, in summary, we have learned structured prediction, okay? And we learned a generative model and a discriminative model to structured prediction. And we learned how to represent the input and output. And we learned decoding. Okay, so we spent, how many weeks did we spend? We spent 5 weeks, okay? Building the solid mathematical theoretical background for NLP and showing the linear models for NLP, okay? From next week onwards, it'll be all neural, okay? So see you next week.